Hey y'all, we are Memphis Community University and we are back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we are going to be continuing our integral journey, our BC integral journey, and we are going to be learning integration by partial fraction decomposition. So keep in mind that this is a BC topic only. If you're in AB, it is unfortunately not on your portion of the AP exam, but you can still join for the fun. It's also on College Calculus 2 exams, but in this video, we're going to keep it generally pretty simple. We're going to only limit the questions to be those that are found on the AP exam. And when we have these fractions, the one on the AP exams have to be terms which are quadratic that you can factor with non-repeating linear terms. Meaning that when we start factoring these fractions, that will appear generally over here eventually, the factored forms are going to be something like x minus 1 times x plus 2, and not, for example, x minus 1 squared, because it would be the same repeating factors. Integration by partial fraction, in my opinion, is a pretty easy process compared to potentially U-subs, which is actually an AB integral form. And what you just need to know is that it's just going to be a process where it requires a little bit of algebra, it requires a system of equations at some point, and eventually you're going to take some integrals of easier fractions, and those will always be ln's. So let's get going with mine as well. We're going to do integration by partial fractions. Integration by partial fractions. Again, I don't think that I'm going to list out steps, unlike my previous videos with integration by parts or U-subs. I'm just going to go for an example, and hopefully as I do the question, I can explain the steps as I go through it. So the questions of integration by partial fractions look something like this. You're going to have something like x minus 1, integral of x minus 1. Let's erase that, x minus 1 times x plus 2. On the top, there's going to be some simple numerator, like maybe, let's say 2x plus 3, and then we're going to have dx. So this is going to be my integral. And my goal is that this integral is quite complicated, and what I want to do is I want to split it up into two simpler fractions, where on the first fraction it'll be something over x minus 1, a number over x minus 1, and then my second integral will be a number over x plus 2. So that's my ultimate goal. So again, I'm going to eventually try to split this up so that it's a over x minus 1, where a is going to be a constant, plus b over x plus 2, where b is going to be a constant, so that these two integrals I can do separately, and they will be easier than my first integral that I'm starting off with. So what you do is, there are going to be constants that make this work, and how you solve for them is you're going to try to go and sort of in the reverse. You're going to take these fractions together with the a's and the b's, and you're going to add them together with a common denominator. The common denominator is going to be this, and you're going to set your new numerator, sorry about that, your new numerator to 2x plus 3. So let's see how this works. So basically what you're going to do is you're going to cross multiply this, a times x plus 2, a times x plus 2, and then you cross multiply this one, plus b times x minus 1, and you set it equal to your original numerator, which is going to be 2x plus 3. So 2x plus 3. This equation will allow me to form two new equations that will be a system of equations that will allow me to solve for a and b. But again, how did I get this? I'm going to add these two things together. That allows for a common denominator. The common denominator is going to be this, and the numerator, by the rules of fractions, will be x plus 2 times this one, x minus 1 times this one. For now, what I'm going to do is I'm going to simplify this a little bit. I'm going to just distribute these a's, form a little bit of a rainbow pattern. So it's going to be ax plus 2a plus bx minus b equals 2x plus 3. And this allows me to form two equations. And what I'm going to say is that there's going to be an x equation and a not x equation. So there's two sides of this equation, of course. So my first new equation is going to be the x equation. Basically, all the x's equal each other. So ax plus bx is equal to 2x. So we can have ax plus bx is equal to 2x. That gives me the equation a plus b equals 2 once I divide by x. So I have a plus b is equal to 2. Finally, I have my not x's equation. So that's going to be 2a, because that doesn't have an x, a minus b, that doesn't have an x, and also the plus 3. So this is going to be my constant equation. Going to be 2a minus b equals 3. So those are going to be my two equations. Again, from this numerator equation, you form two new equations. One of them is the x one, so all the x's are equal to each other, and also all the not x's, or all the constants, are equal to each other. And that's this equation right here. Once you have these two equations, you can solve them in any way you would like. Perhaps substitution, perhaps elimination. This is Algebra 1 stuff, and we love Algebra 1 stuff. Nice to think about fond memories, of course. I think the easiest way to do these integrals will be to eliminate the variable b. So it looks like we're going to have 3a is equal to 5 once we add these two equations together because the b's get eliminated. So that means that a is equal to 5/3. Again, it's pretty simple Algebra 1 techniques here. When we plug in 5/3 into b, into this equation to solve for b, it's going to give you 5/3 plus b is equal to 2. So what's b? Well, b is 2 is 6/3. 6/3 minus 5/3 is 1/3. So it looks like we have our a and b here. Of course, that's not the answer, but again, our ultimate goal is to break up these integrals into two easier integrals. And how we did that is we set an equation, we set up from that equation, we set up two new equations. One is the x equation, one is the not x equation. We solved this mini system of equations, got these lovely variables, if I may say so, a and b. So what we're going to do is we're going to replace the a with this guy right here. So it's going to be 5/3 instead. 5/3 x minus 1. Now that we know b, we don't need b anymore. We're going to replace b with what it is. That's going to be 1/3 x plus 2 times dx. So remember that whenever I have constants, I always like to take the constant outside of the integral. That just makes my life easier. And sometimes my life is a little bit difficult, so I want to make it as easy as possible. So I did have a 5/3 here because that's what a is, but I'm dragging it out of the integral. It's going to be 5/3 times dx. Same thing with 1/3. I like to take up my constant because it makes the integral a little bit easier to do when I take the antiderivative. So it's going to be this. 1 dx or dx, we're going to save some space, so I'm putting dx right here. So this is what I'm going to do for all the other ones. Once I solve for my a and b, I will replace the a and also take it out all in the same step because it's an easy step to do. And then keep in mind that every time you're doing these things on the AP exam, integration by partial fractions, what will happen is that you'll have ln's because you're going to have these linear terms, so then the integral of them are ln. So in this case, it's going to be 5/3 ln of x minus 1, because the integral of 1 over x minus 1 is ln of x minus 1, technically an absolute value. And then finally, what's the integral of this? It's just the constant, 1/3, then it's going to be the x plus 2. So x plus 2, and then we can write plus c. Hopefully you can see my work here. Like usual, I'm not very conservative with my space, but that's how you do it. So again, these questions do involve a lot of work. They sometimes appear on free response questions, and because they involve a lot of work, they're worth like 4 or 5 points. But I'm always willing to do them because while this might be a cumbersome process, it's not a hard process. But let's explain what we did. Let's recap just to sort of relive the fun. So if we had this harder integral, we notice it's integration by partial fractions. So what we do is we want to break it up into simpler integrals, simpler fractions. What we need to do is we need to solve for this a and b. And how we do it is we cross multiply. So we're going to have a times x plus 2 plus b times x minus 1 equals the original. Then you set two new equations. You're going to have an x equation. So it's going to be ax plus bx is equal to 2x. That gives me that a plus b equals 2. And then you have your not x equation. 2a minus b plus 3 equals 3. Then you use your system of equations, either substitute or eliminate. In this case, it was easiest to eliminate. We added these two equations together. We got that a was 5/3, we got b is 1/3. And those are important constants. We replace them with where they go, and we take them out. And then when we take the antiderivative of, again, these two simpler integrals, which is the entire point of this process, then it's always ln. We took the ln, and then we finished the question. So notice that these two integrals are very simple, but you need to find a and b so that these are able to be broken up legally. So that's how you do the process. I'm going to talk a little bit about these simpler antiderivatives. It's going to be a recap of our use of video or our integration by integration AB review. But keep in mind that the integral isn't always perfectly ln. There could be a constant in the front because of a use of. So when I have this, eventually I might have some constant, we can just call it a over x. The integral of this one is definitely ln because the integral of 1 over x is ln of x. So in this case, it would be a times ln of x plus c. And like we saw before, the integral of something like a over x plus 1 because the derivative of x plus 1 is 1, this integral is going to be a times ln of x plus 1. But keep in mind that when we have these terms, it might not be this easy. For example, we might have something like a over 2x plus 1. And you might think that, well, the integral would just be the same sort of thing. It's going to be a times ln of 2x plus 1 plus c. But you would be wrong, unfortunately, because this does require a u sub, because the inside function is 2x plus 1. But we can skip these easy u subs as we talked about in our AB integral review. So what's the integral of this? It is going to be this, but we need to multiply by the reciprocal of the derivative of the inside function. So it's going to be 1/2. If you want to do a lot more work, you could say u is equal to 2x plus 1. You could say du is equal to 2 dx. Then you can change this integral in terms of u, where the important thing is that you'll have a 1/2 in the front. But with these easy u subs, remember, you just take the antiderivative, and instead of the chain rule where you multiply by the derivative of the inside function, you multiply by the reciprocal of the derivative of the inside function, because you're taking an antiderivative. So for example, if you have something like this, a over 5 minus 7x, it's not that hard of an integral. All you do, if it's linear, which all these partial fraction things end up with things that are linear, you write your a, you write your ln, you put the thing in the denominator in parentheses here, or absolute value. But just don't forget to multiply by the reciprocal of the derivative. So in this case, the reciprocal of the derivative would be -1/7, because the derivative of 5 minus 7x is -7. So I'd multiply by -1/7 here. In general, again, we're going to have things of the form a over mx plus b times dx. So what's going to be the integral here? It's going to be ln of mx plus b, the thing in the denominator. There's going to be an a in front. And what we're going to do is we are going to multiply by the reciprocal of this derivative of mx plus b, but that's m, it's the slope, it's the derivative, it's all those fun words. It's going to be 1 over m. So just keep in mind that after we do the integration by partial fraction process, meaning we find the a, we find the b, we take out the a and b, we're ready for antiderivatives, what fun. As we do that, we do need to multiply by the derivative of the inside function, 1 over m, as we take the antiderivative, if the ln is not as simple as it looks. So let's practice one of those. So I'm gonna erase this, erase this, erase this. Let's get going. Let's do a new integral. Let's do the integral of 2x plus 1, x minus 1. And then what do we want at the top? Let's try to do x plus 3 on the top. So this is what partial fraction decomposition integrals look like. Something that is factored on the bottom, and then some linear thing on the top. And again, what will be our eventual goal is to split this guy up. These two guys don't like each other, so we're going to keep them away from each other. It's going to be a over 2x plus 1 plus b over x minus 1. But unfortunately, for legal reasons, we're not allowed to just split up the fraction however we want. We do need to make a and b particular numbers so that when you add these two fractions together, you will get x plus 3, and that's the system of equation business. So what we're going to do is we're going to cross multiply here. We're going to get a times x minus 1 plus b times 2x plus 1. And then you set it equal to the original, which is x plus 3, x plus 3. From here, hopefully you can see that there's going to be an a equation, not an a equation, an x equation, which involves a and b's, and a not x equation, which also involves a and b's. So it's going to be ax plus 2bx is equal to x. So I think that's going to be ax plus 2bx, where I'm not going to write the x's anymore, equals 1. So this is my x equation. Then I look for my constant equation. Again, you need to distribute, so it's going to be minus a plus 2b equals not 2b, 1b, sorry about that. I'm doing my not x equation, so it's the minus a plus b equals, what's the not x on this side, what's the constant on this side, 3. So again, this is how you set it up. All the x's need to be equal to each other, and all the not x's have to be equal to each other. So a plus 2b equals 1, ax plus 2bx is equal to 1x, and then finally minus a plus b equals 3. So now what we're going to do is we are going to solve this system of equation however you like. Again, I think the easiest way will be to eliminate by adding these two equations together. You could substitute if you always love substituting. Definitely a great system of equation method, but in this case, the easiest way is to eliminate, just add these two equations together. Looks like you're gonna get 3b is equal to 4, which makes b equal to 4/3. And then for a is equal to, well, if we bring the a back and then the 3 back, this is all just algebra 1 business. It's gonna be b minus 3. A is b minus 3, I believe, which is going to be 4/3 minus 9/3. It looks like a is negative 5/3. So that's going to be negative 5/3. So now we did all the algebra 1 business. Now we are ready for the calculus business. So again, we're trying to split up this integral because splitting up the integral is always a good strategy. And these a's and b's allow us to split up the integral. When I do this, I have the a as negative 5/3. You could put it right here, but again, I like to take out the constant. So I'm going to write it right here, negative 5/3. And I'm just going to write the original 1 over 2x plus 1. Same thing with the b was 4/3. I could put it in the numerator here, but you're allowed to take out constants, so why don't we exercise our right for freedom? We're going to take that 4/3 out and write 1 over x minus 1. So now we're ready for ln's. So again, on the AP exam, these have to be linear. On college calculus exam, sometimes they're quadratic, so it's a little bit trickier. But on these, they have to be linear on the AP exam, so these will always be ln. So in this case, this one is easier. 4/3 ln of x minus 1 is this guy right here. We'll add the plus c at the end. And then this guy is again slightly harder because of the discussion we had earlier. The derivative of 2x plus 1 isn't 1, so we do have to account for it, but it's not too bad. Just write your constant, negative 5/3. Write the ln of this thing, 2x plus 1. And then we do need to multiply by the reciprocal of the derivative of the inside function. The inside function is 2x plus 1. What's its derivative? Of course, that's just 2. So we need to multiply by 1/2. So this is the u sub in your head, or skipping the u sub, or doing the reverse of the chain rule, all these things. You just need to make sure that you have this 1/2 here, because that's the antiderivative ln of 2x. If you want to, of course, you could do a u sub. U is equal to 2x plus 1, du equals 2 dx, and so on. But just make sure that you have this 1/2. It's not always just ln, it's ln of the denominator, maybe times some sort of constant here, depending on what is inside the ln. But this is the integration by partial fraction process. Hopefully you can see it's not that bad. It is quite long. You do have to cross multiply. You do have to set up equations. You do have to remember your middle school days or your early high school days where you solve this system of equations with elimination or substitution. But then once you do that, the integral itself isn't very hard. It's easier than integration by parts or integration by u subs. Let's do a few more examples. Sometimes it's a little bit less complicated than the numerator, but sometimes people get confused with that. So let's try one of those. So I'm going to erase this. I'm going to erase this. Let's do a few more examples because we're having so much fun. Let's do the integral of just the number 3 on the top, dx. And then we're going to have x minus, let's actually have something that's not factored. So let's have it x minus x squared, something like this. So the first step you have to do when you see something that is integration by partial fraction decomposition is that you do need to factor it. If it's not factored already for you, unfortunately you do have to do that one step of factoring, but in this case it's not that bad, of course. We're just going to take out an x. So it's going to be the integral of 3 over x times 1 minus x. Nothing too crazy. So again, our end goal will eventually just be split this bad boy as a over x plus b over 1 minus x, where when we add these two fractions together, we'll get this original one, where so a and b has to be particular things. And how do you find the a and b? Well, what you're going to do is you're going to cross multiply a times 1 minus x plus bx, and then you set it equal to the original numerator. In this case, it was just the number 3. So I'm just going to write 3 here. So I have my nice little equation. I'm going to not look at this at all. I'm going to try to solve for my a and b just like before. And then once I have the a and b, I'll replace them into this guy right here. So keep in mind that we are going to solve for a and b. That is the goal here. So let's try to set up our x equation and our not x equation. So our x equation looks like it's going to be minus ax. So I'm just going to write minus a plus bx. So I'll write plus b. But if you notice on the other side, there's no x's. But that's going to be okay. That just means that it's just equal to 0 x's. So minus ax plus bx minus ax plus bx is equal to 0x. So I have minus a plus b equals 0. Then we're going to do our non-x equation, which is our constant equation. Looks like that's going to be a, and then it looks like we don't have any x's here, so it's going to be a is equal to 3. So notice that we have a pretty simple equation here. I'm definitely not going to complain about that. A is equal to 3. That means that, of course, we can solve for this, but it looks like b is also equal to a if we bring the a to the other side. So that means b is equal to 3. So nothing too crazy here. It was easier because this term is so easy, and also there was no x's on this side. But again, don't get confused if you don't have any x's. You can still form an x equation. Minus ax plus bx is equal to 0x. A plus 0b is equal to 3. Just all your x's together on both sides, and then all your not x's or your constants together as well. So then once you have these numbers, again, you're basically done. We're going to replace the a with 3, but we're going to take that 3 out just like normal. So it can be the 3 integral of 1 over x. I will deal with you later, but let me plug in the b now. So it's going to be plus 3, because I replace the b with 3, and I take out that constant. So it's going to be dx over 1 minus x. Now we're ready for the antiderivative, which is always ln, perhaps, times a constant. So this first one is the most classic example. Always nice to see the classic, of course. So this can be 3 times ln of x with absolute value. And then just keep in mind that this one is slightly tricky. It is also 3 ln of the thing in the denominator, 1 minus x. So 1 minus x. But again, we do have to account for the derivative of the inside function. So it's not going to be plus here, even if this is separated by a plus, because we do need to multiply by -1 and technically divide by -1, because you always need to multiply by the reciprocal of the derivative of the derivative of the denominator. The denominator is 1 minus x, its derivative is -1, so we need to multiply by the reciprocal of -1, which itself is -1. So that's why this is a minus here. And then what you're going to see is that sometimes when this is a multiple choice, they're going to try to simplify the equation as much as possible. Remember, if you have two ln's that are subtracted and the number in front of them are the same, basically we can distribute out of 3. That ln subtracted, the 2 ln subtracted becomes division. So in this case, we can do one extra step. We can write this as ln of x over 1 minus x plus c. Just don't miss the question because you can't see that your answer is actually right. You just have to convert it to potentially the answer choices that are on the page. But hopefully you can see that this question wasn't any bit more difficult. Even if this were just dx here, then the entire system would be the same, except that we would be setting a to be equal to 1 when you have just one dx on the top here, because it'd be 1 dx. So if you have no x's, it's okay. You can just set it as 0. The x equation is 0. Negative ax plus bx is equal to 0. If you have no b's, that's okay as well. Just all your constants equal to each other. The hardest thing, in my opinion, is that when you take this antiderivative of 1 over 1 minus x, you do need to account for the negative, the chain rule, or the opposite of the chain rule, technically, because you always need to multiply by the derivative reciprocal. But that's it. That's how you do indefinite integrals with partial fraction decomposition. I don't think it's any harder than normal. You never have to do it twice, for example, like integration by parts. You never really need to know how to start the process like u-subs. You don't have to choose anything. So I think that this is one of the easier integral methods if you're willing to carry out all the steps. And again, they are annoying, but we are going to do that. So to recap or to conclude this video, let's try to do some with definite integrals, meaning that we'll have numbers now, but you'll see that it's not any harder. There's not really a new method. You just do the process and then you plug in top minus bottom like normal. So let's try to do another one. So I'm going to do that here. I'm going to do that here. So let's do something like the integral of, let's keep it simple. Let's try x squared minus 4. And then we'll have x plus 3 on the top. And now we're going to add numbers. So my numbers are going to be 3 and 5. So now we just have numbers, but again, it's going to be the same process. We're going to do the a and b process, set up the system of equations, solve it. And then what we're going to do is we are going to just, at the very end, after we take the antiderivative, we're going to plug in top, we're going to plug in bottom, and we're going to evaluate. The answer will probably be in terms of ln's. So in this case, again, if it's not factored, you should factor it, but x squared minus 4 might be the most famous thing to factor. It's x minus 2 times x plus 2, of course, from difference of squares. So it looks like this integral is going to be from 3 to 5, x plus 3. Oh, we don't want it as x plus 3. We want it as a over one of these. And then b over as one of these, because that's the point of partial fraction decomposition. We're decomposing the original integral into partial fractions, so that's why it's named nicely. So we have this. Then we do our cross multiplying action to set up our x equation and our not x equation. They will both include a's and b's. So it's going to be a times x plus 2 plus b times x minus 2. What are we going to set it equal to? Well, it's going to be the original numerator. That looks like it's x plus 3. Then we're going to do x's and b's. Let's try to combine all the x's. So it's ax plus bx is equal to x. So it looks like it's going to be a plus b is equal to 1. Not the hardest equation in the world. Then it's going to be 2a. So it's 2a minus 2b is equal to 3. Because those are all the not x's. 2a minus 2b equal to 3. Then you solve your system of equation. Again, you can substitute if you want, but it looks like if I multiply this first equation by 2 and I add the equations together, I would eliminate the variable b. So that's what I'm going to do. I'm going to multiply everything by 2. I'm going to be careful. I'm going to add up all the equations. The b's cancel, so that's why I'm doing this. Looks like 4a is equal to 5. So a is equal to 5/4. Nothing too crazy here. Originally, a plus b is equal to 1. So 5/4 plus b is equal to 1. That makes b negative 1/4 because you have 5/4 and you want to subtract off a fourth, you'll end up with 1. So b is equal to negative 1/4. So it looks like we are ready to go. Let's try to take these a's and b's and place them where they're supposed to go, taking them out of integrals. So it looks like it's going to be 5/4 the ln of x minus 2. I skipped a step, but let's just change it here. The a is going to be 5/4, so I'm going to just take that out of the integral. And then the b, when we have a separate integral, so it's going to be b, we're going to take out the b, so it's going to be negative 1/4. So let me erase this real quick. It's going to be negative 1/4, sort of running out of room here. The integral from 3 to 5 as well, 1 over x plus 2 times dx. Again, it was b, but we found b to be negative 1/4, so we took it out. So in this case, it's going to be negative 1/4 ln of x plus 2. And then we are going to, instead of writing plus c, we are going to evaluate it at 5 and 3, because that's what the fundamental theorem of calculus tells me to do. And I always follow the fundamental theorem of calculus. I never question it. So I plug in 5 and 3. If it tells me to do something, I do it. So when I plug in 5 and 3, of course, you're going to be careful with top and bottom and stuff like that. So it's going to be 5/4. Looks like it's going to be ln of 3, because it's 5 minus 2, that's 3. Ln of 3 minus 1/4, ln of 7, minus, and then when we plug in 3 here, looks like you get ln of 1. That's lovely, because the ln of 1 goes away, so we can just sort of mark that out. Then you get minus 1/4 ln of 3 plus 2 is 5. So you get 3 plus 2 is 5. That's the ln of 5. And if you want, you can simplify this a little bit more, but I think this is simplified enough. Again, when you add these numbers to make it a definite integral, nothing too crazy. It doesn't really change very much. So in this case, the answer is 5/4 ln of 3 minus 1/4 ln of 7 plus 1/4 ln of 5. But again, the process is exactly the same. You first break up the fractions. You write a and b. You cross multiply to form this equation right here. You set it equal to the original, and then you solve your system of equations. Once you have your a and b, you replace it and you take it out. When we were doing these integrals, they was actually pretty simple, because when we took out this 5/4, when we took out this negative 1/4, the denominators had nice derivatives. They were just 1, so we didn't have to multiply by that number in the front. So all we did was we took ln's, and then we plugged in top minus bottom, and then we were finished. So that's integration by partial fractions. Nothing too crazy. So again, what you do is you break it up. Then you have a and b, or a and b, depending on how the camera is. You set up an x equation. You set up a not x equation by cross multiplying and setting it to the original. You're going to solve that system of equation right here using elimination probably. Then you replace your constants. Where do they go? Take them out of the integral, and you should have two separate integrals by then. Once you take the integral, it's always ln, but just keep in mind that it's not always exactly ln, but it's ln times the derivative of the reciprocal of the derivative of the denominator. So in this case, we multiply by 1, but if, for example, you had 1 over 3x plus 1, that antiderivative would be 1/3 ln of 3x plus 1. Then, if you need to, you can do log properties if you want to make them a little bit prettier, the answer, or you can plug in top minus bottom to evaluate the fundamental theorem of calculus. So that's integration by partial fraction, and it's not too bad. Keep in mind, though, that perhaps the hardest part about the BC exam, or when you're doing integrals in general, maybe just for fun, it's hard because you have to determine which integral process to do. So these are the ones that are integration by partial fractions, but you have to be wary that it could be u subs, for example, it could be something else. So let me just show you two integrals that we did previously, but you would not want to do this process on. And how do I know that you don't use this process? I will tell you why. So, for example, you wouldn't do the process on this guy right here. One is that, again, all of the denominators on the AP exam can be factored. So because you can't factor this, it's probably not partial fraction decomposition. It's just going to be a u sub. U is equal to x squared plus 1. du is equal to 2 times x times dx. So we have an integral here, which is 1/2 in the front because we're solving for x times dx. We have u and the denominator du. So this becomes 1/2 ln of u plus c, which is 1/2 ln of x squared plus 1 plus c. If you want more explanations of this, then be sure to check out our u sub videos. But again, this is a u sub because you can't factor the bottom. You cannot do the a and b thing. You can't set up a system of equations because you need to be able to factor the bottom. Same thing with something like this. So keep in mind that if it's reversed, well, we can actually like it better if it's reversed. This is what we call the split numerator. You do not do, again, the process because on the process of integration by partial fractions, the bottom will be some sort of quadratic. So this one is split the numerator. So we have x's, and then we start doing stuff. We cancel these out. We take the antiderivative. This was in our first integral video, which is called basic integrals, x squared over 2 minus ln of x plus c. So notice that sometimes you're going to encounter fractions, and not every single fraction is partial fraction decomposition. But on the BC exam, you can be sure that you'll probably do partial fraction decomposition at least once, perhaps on the multiple choice, perhaps on the free response questions. Hopefully this made sense, this video. Again, cross multiply your things after you separate, set up an x equation, set up a not x equation, use system of equations to solve it, then take the ln of both things once you're ready to replace the constants, and you take them outside the integral. Keep in mind that it's not always ln, it might be ln times a certain number, the reciprocal of the derivative, and that's all it is. But if you want more practice on this, please be sure to check out our Girls Teach Calculus video, which I'll link in the description below, where one of my former students goes through several of these examples, some where she has to be careful with the antiderivative, with the ln's, where she does all these system of equation businesses, some where there's going to be definite numbers, and she even has a few split the numerator and some, so that you'll be able to spot when you actually don't use partial fraction decomposition, because that is as important of a skill than using the process. Hopefully this video was useful for you. We do have another video after this, and that will be our total BC integral review video. So in that video, I plan to do a few questions. I'll do a partial fraction decomposition question like this. I'll do some u subs. I'll do some integration by parts. I'll do a split numerator. So be on the lookout for that if you want a comprehensive review on all the integrals that might appear on the BC exam. But until then, thanks again for watching like normal, and I hope to see you next time.